Yeah, welcome to our CeADAR Tech Talk. So for the Tech Talk today, we are going to have a talk on the topic of the current progress of AI in medicine and how to apply it. And the speaker is Professor Dubravko Kubrick, the director of the AI Institute of Serbia. So I hand it over to you, Dubravko.
Thanks. Let me just cover this. Well, before I start, there's something I've always wanted to say. Top of the morning to you. Okay. So today's Stack Talk, and I've looked at a few of them, and I see there's different focuses and so on. I'll talk a little bit. It's not going to be too much about research. I'll present one topic that is research, sort of purely, although I guess all AI is applied research, but I'll mostly focus on two things where we are kind of applying cutting edge research to real life applications in medicine, right? And let me see if my slides are okay. We titled it this. These days, I don't do as much science as I would like to. Mostly I manage people, but so there are contributions from various research leads and researchers from the institute here. My day job is being a prof in teaching machine learning at the Faculty of Technical Sciences, and then I guess my other hat is the director of the institute. And I guess, not sure what the audience is. This is our sort of a cover slide where everybody's obviously expecting a lot from AI. And this shows in the world around us, there's a bunch of applications that people are doing. Maybe this one on the top is something that I'm actually going to talk about that we do at the institute. Now, in terms of the market forecast, it's not super important, but just to give you a sense of why people are so excited about all this. So it's going to be a huge market, but the important thing, I guess, for us researchers is that the various European funding agencies also view it, and also the private sector view this as a topic that is of interest. So it's not only for the common folk that they are focusing on it, right? And now, what is sort of interesting is that there's, or at least predicted, there's going to be a huge market for AI solutions applied to medicine. And if you know about these compound growth rates and things like that, then you'll see that these are really, excellent projections. But what I kind of like to take a look at is what people are thinking in terms of which applications of AI are actually going to take the most of the market in the years to come, right? And when you look at it, sort of, I guess computer vision is the most mature technology, and it's been applied in medicine for ages, right? With the advance of deep learning, it's getting the things that we can do with it are getting more and more complex. So that's probably going to be the largest share of what we do in the future, right? And of the market. Then, of course, LLMs are making a dent, right? And the third one that was sort of traditionally totally not related to AI in any sense until AlphaFold of DeepMind came out and started folding proteins, right? Was the drug discovery market. And why I've actually sort of, highlighted three of these is because I'm going to show you an example of the project that we do at the Institute in each one of these, right? And actually, I think they're gonna go the same in the same order. So we'll talk a little bit about the medical imaging use case that we've done locally in Serbia. Then we're going to talk a little bit about something that we're doing purely kind of research, but applied in terms of helping and developing new aspects of these virtual assistants and generative AI, LLMs. And then finally, I'm going to talk about how we're actually helping a US-based biotech company develop new drugs using AI and what it entails. And so in terms of technology, from the standpoint of AI, now, of course, everything is machine learning, mostly everything is machine learning, but then NLP and computer vision are kind of sort of looked to as the the things to apply first, right? And I'm sorry, I keep clicking on this. And just to give you an idea of how hot the topic is in terms of research, if you go to the site of Nature, and I did this in April. I did a talk on this topic, and I was too lazy to do it now. But in the last 5 years, there's been more than 24 review articles that are just talking about, and perspective of articles that are talking about artificial intelligence in medicine and how to apply it in different aspects of that. So definitely something that we want to do. Why we do it at the Institute for Artificial Intelligence, or as we call it, IVI, because that's the abbreviation in Serbian. Basically, there are two things that our government is investing in science-wise, and one is the AI part, but probably the bigger national investment is something called the Biofor, which is basically a biotech campus, right? And the institute is a new entity set up only 3.5 years ago, but from the start we were kind of tasked with developing, let's say, talent to support the activities of Biofor. So everything to do with biomedicine, biotechnology, bioinformatics, and even biodiversity, right? And now that we have like 60 plus people and so on, we actually run scientific projects, but also commercial projects. And because we're a fairly small country, right? Then we usually support the government and then our international partners running national level pilots and deploying applications at that level, right? And one of the things that we asked to do is to try and develop a sort of an open system where we could deploy AI tools to help our radiologists analyze breast cancer screening images, right? So it's called mammography, a technique that is the top technique to kind of diagnosing breast cancer early on, right? And that's when it's most treatable for various kind of cultural reasons and I think the lack of radiologists, we actually have a high incidence of this disease and a lot of mortality. But even worldwide, it's sort of the second leading cause of cancer deaths among women, right? And it is, you'll see some of the images. If you're not an expert, it's hard to kind of figure out what's going on, right? And this makes it also a challenging task in terms of people get tired, people do mistakes and so on. Recently, very recently, a few months ago, there was a few studies done and published in let's say Sweden, who is leading in terms of breast cancer screening, and they tried usually the diagnosis of whether somebody should be tested further and so on. is done by 2 radiologists. They tried employing an AI tool, a generic one provided by whatever company, right? And together with a single radiologist, they actually they were 4% more precise, right? More accurate in the work. And of course, it costs way less, and they were able to handle way more patients, right? So this is what we're kind of trying to do. And it's a sort of an extension to the new deep learning domain of the different sort of computer-aided diagnosis software systems. They are typically that exists if you buy any kind of mammography screening or mammography machine, you like imager, you'll get a software from whoever produces, whether it's Hologic or Fujitsu or somebody that already tries to apply some computer vision things to kind of make your task easier, right? And so just to understand,
So sorry, is that audible?
I think the
Mark,
browser is
yeah.
frozen.
Oh, yeah.
What did I do?
Yeah, no, it's
Okay, now
perfect. Yeah.
you were frozen earlier.
Sorry. All right. And so basically you are supposed to, as a radiologist, see all these things, right? And come up with an opinion on whether this is something that should be addressed and what kind of therapy to do, right? And so the go-to, I guess, technology in deep learning is the convolutional neural nets. I hope that everybody kind of knows what they are, but they are basically neural network architectures that they're designed for image processing and learning stuff from images. There are newer architectures around, but these are, let's say, the most stable and the most tested, and most pre-trained models come in this shape and form, right? Our idea was the original data sets that we looked at had tens of thousands of images, right? That doesn't mean that not all of them, thankfully, are have an issue, right? So a smaller amount of those annotated actually had some issues that needed to be detected, right? But we were working with our National Institute of Oncology and Radiology, and they were kind of you would typically label the image in terms of something that's called BIRADS, which sort of, if you are BIRADS 0, then you're kind of you're good, right? All the way up to 4, you're fine. 4 and 5 are where we should get worried and probably treat people and so on. So our partners wanted us not to go for this fine-grained thing. I think because it turned out that this sort of annotation is no longer the way they do it in their own area of research, right? So we had to kind of take a model that or data set that was designed to train for these things, different BIRADS, and make it a binary decision, which kind of entails all sorts of problems with it, And the other part of it, one part of it was taking the state-of-the-art stuff, right? Usually done by postdocs or PhD students, and kind of make it into a software that does something, right? Or model that does something. But then we actually had to, get our hands dirty and deploy it in our national data center and actually create the whole of the, simple software that radiologists all across the country can use, right? And so we opted for a VGG16 convolutional neural net. And these are the two main data sets, that the open data that we could find. But then often we'll find that the stuff collected somewhere, and these are US based, will not exactly work out of the off the shelf for local stuff, because there are different genetics and so on. And then so we basically got together with our partners. We took thousands of images they process every year just for the year 2020, right? It took a little bit of sort of their information system doesn't store it in an ideal way. You have separate places where the images are stored, and then separate databases for the opinions of the radiologists, and they're not really ideally synced. So there was quite a bit of work to create something that is representative, right? And then we in the end ended up with like a little bit over 3K images, but with a sort of balanced set of truly positive things and that we want to detect, and things that are kind of that we don't want to detect. But we opted for something that's called BIRADS 2, which means they are negative, but it is something that is close to the edge of the decision boundary, right? And we're not bad. We're kind of area under the curve is under the rock curve is 0.8, which is really good, but we wanted to push that further. And then the other thing that we were kind of faced with, we could not really sort of completely do away with basic old school computer vision, because you would have all sorts of different tags and things that would show up on the image, right? The radiologist at image in time place on the machine, right? So the first thing that we had to do, and not every machine would store it in the same format, in terms of sometimes the breast tissue would be black on white, right? Sometimes it would be inverse. So the first thing was to develop a few simple things to sort of housekeeping and pre-processing stages. So we would invert all the images if they're not, in the color scheme or grayscale scheme that works for us. We would then do a bit of segmentation and extract the largest blob, because that kind of does away with all the artifacts and tags and stuff that they would do, right? And then we would just feed it to our model, right? But then as soon as we deployed it, we figured out that sometimes there's going to be an image that is maybe a pathology sample, totally not breast tissue, or an image that is so that the placement is wrong and things like that. So we actually had to implement a model that would first detect that an image is sort of out of distribution for our main model, right? And then if this is the case, we just highlight it and tell them that this is not something that we can work with, right? And this actually is a sort of a very important, let's say, ethical concern for the deployment of it, because even if all the images are sort of at the time of testing exactly what we expect, what happens if there's a new machine, something happens, we start getting images that are not what the model was trained on, we need to know, right? So we'll be monitoring in the deployment the distribution of the images, incoming images, and if we see that there's quite a few examples that are not really fitting it, we'll try to retrain the model and see what's going on, right? And this is done super easily if you know the Fréchette interception distance, FID, typically used to kind of evaluate the quality of visual generative models. We use that to actually filter out the output distribution stuff. And in the end, it's a sort of application. But the first thing that a radiologist is going to tell you is, okay, so you think this is 100% lesion that needs to be looked at, right? Why do you think that, right? And where is it located? So we ended up actually taking one of the recent sort of XAI models. And so once we train our basic model to do actually the classification of the mammograms, we then train another model that learns together with it to kind of highlight the parts of the image that correspond to the largest activations of the last layers of our neural net, right? And that kind of provides for us a heat map saying that these are the regions in the breast that our model thinks are those that should be looked at, right? And that it bases its decision on, right? And I actually, for all the other projects, I had a video, and I'm sorry, it's kind of weird because we were not, we were doing it last minute, and there's personal data that we cannot show, right? But what you see, and what you'll see is, in the first images, you'll see a real sort of mammogram, and with the XAI part indicated in red. And then the latter part is what we are doing now is asking the radiologist to verify our model, right? So they'll be looking at the output and actually telling us that, whether this is okay or not. They also told us something that for a deep learning guy is super counterintuitive. When they judge if there's a problem or not, they're kind of using some basic features such as symmetry and some micro classification and some shadows and things like that. So 4 things that are important to them, which don't really exist in the open source data, right? And it's sort of not the way we do computer vision anymore. So we would not, try to design the feature. We're trying to learn them end to end, right? But they insisted, and then we let them, when they see that there's a problem, they're going to actually indicate why they think that's a problem. So hopefully with this, we'll get a much more high quality data set, right? Much higher quality data set that we can, both use to verify our model, but also fine tune it, right? And so, sorry, I'm doing it again. I don't know why. And then I like to switch to. So this was a pure computer vision thing that we're doing, right? And the second part is pure text generative AI project, actually research project that was financed by the Horizon program through the next generation internet search project, right? So kind of a cascade thing, and it finished a couple of months ago. These days, the LLMs, they'll still do the stochastic parrot and generate things that are not really true, but it's a little bit less than it used to be, right? When it started out, we were working already with Bayer on a zero-shot classification in medical texts, right? To kind of help them identify new compounds that they could use for drug development, right? And of course, everybody wanted immediately with the advance of LLMs to kind of have a chatbot to search through the literature. The problem there is that, even if it doesn't have the right answer, right, it will provide something, right? And that actually, when you're doing research for drug development, is a very bad thing to happen, right? Now, just to make it a little bit more, interesting. The guys did a promo video for the project, and so before I dive into that, I'll just let it play out. I think it died on me, which is not the ideal thing to happen, right? Let's. There we go. I'm sure you can view it. There's going to be a link later. But basically, as I said, it's a big problem in the biomedical domain when you don't get accurate and factual answers. And as you all know, probably LLMs are not really trained for that. They're trained to provide you an answer, whatever happens, right? And so the typical way of addressing this and sort of anchoring them in reality is something called retrieval augmented generation. I don't know if and how many people know about it. It's sort of a framework that came out of Meta, Facebook, and the idea is that if you can, sort of provide to the agent a database of knowledge, right, a small one that it can feed on, then you would get answers that are, both more strictly to the domain, but actually more accurate in terms of what it's saying, right? And what we did in this project is that we added sort of a layer on top of that, where another model is actually going to look at what the original generative model is saying and try to decide and kind of weigh in terms of how much this actually corresponds to something that can be seen in the literature, right? And progressively diverges from that. So when you are doing research, what's a hard fact, what's somewhere in the middle, and something that you really need to check for yourself in the references before you do something, right? And so the part on the left, everything was done on PubMed data, which is a public data set of medical papers, right? And we implemented a RAG thing where it actually has a vector database of different papers, and from the data, they would we would actually cluster that to make it easier, and then where the magic sort of happens is we sort of came up with our own question answering, PubMed question answering reference data set, where you can kind of have answers to the questions that are verified and good. So once you would ask something of our LLM, right, you would get not only a response, you would get something that these days, people moved in the same direction. These days, when you get a response from the LLM, you usually get a number of references to check that let you check stuff, right? In our case, there are real references from the PubMed data and the papers. Because sometimes early on, let's say ChatGPT would generate a beautiful text with all the references, but none of the references would exist in real life, right? This prevents that from happening, right? And then on top of it, when we get an answer, we would look at the psi fact that this is a data set that has a set of human-generated scientific claims and abstracts from the papers that support them, right? And it's trained to kind of actually detect entailment, which means that it asked, it gives a number of saying how much a statement corresponds to the abstract, right? So we would get the abstracts that are most relevant to the query asked, right? And once the generative part is done and we get a response, we would also check how much this response corresponds to the actual references, right? So it's sort of, instead of you checking the references, there is another agent, an LLM, doing it for you, right? And once it's done, well, I went through this, so maybe just skip it. But once it's done, what it really looks like in when you're using it in implementation, you would get answers of this sort, right? That sort of the green stuff is something that is definitely true, right? And then the yellow stuff is something that you would kind of want to check out, and then you would get sort of, you know, what exactly and where in the abstract is this derived from, probably, right? So you can immediately look at the actual text and kind of judge for yourself if this is true based on that, right? Which is what the models usually. And so it's a little bit of a tool to support our buyer friends when they're looking at the medical literature, and as in every domain, there's more and more papers, so we really need agents to help us with this. And then I'm kind of trying to be mindful of the time and what Kwon told me to do. The last one is something that we do, also applied research. For a biotech company, we are actually using AI to design drugs. This is a sort of a peptide therapy, which is sort of the frontier of medicine in a way, right? And why we actually do it, well, let me show you how we do it, and then I'll talk a little bit of why we do it. And hopefully this works this time. Oh, sorry for that. So why we actually do it, I'll come back to this. Oh, do I have it? Oh, no, not right. Is the fact that there's something that the guys in the pharma industry call Irum's law, which is basically Moore's law inverted. And actually, the more money they're putting into development of new drugs, you get less bang for your buck as the time progresses. So it's beginning to be harder and harder to find new therapeutic compounds, right? And so the idea behind using AI is to do what they call an in silico drug design, which basically just means you run it on a computer instead of trying out things in a so-called wet lab where you're actually, trying how these chemically trying to bind these new compounds, right? And so the first thing they have to tell you what they would actually like to treat, whether this is some connection they would like to inhibit or something that they would like to add to this and so on. And then you kind of have to do a manual dive into the lit review, right? Maybe using the Verify AI to make sure that you're not wasting a lot of time, right? And kind of figure out exactly what you would like to design, or the compound that you would kind of, let's say, a lock that you would like to find a key for, right? And then you can use AI and machine learning and models to first of all create sort of a scaffold. They call it the backbone of the structure. And then that sort of gives you an idea of what the molecule should look like, right? But that doesn't mean that it can really exist in the world, right? So, and in our case, as we are dealing with the peptide therapy, we actually are looking to build well, it's called polymers, but basically large molecules of amino acids, right? Not so large because they need to be a peptide. It needs to be less than 40 amino acids, but it's still a organic molecule, right? And so once we have the backbone, we have to figure out which amino acids can kind of fit it and make it fold that way, right? And once we try to fold it, then we have to see if this thing that the model guessed can actually bind to the place that we want, right? And this involves the part where we actually estimate the binding, the so-called binding affinity. The lower the value that the score that we get, that means that we get a better fit for our task, right? And then these things, tagging is something that we don't always do. It's done manually. Basically, you would add small organic molecules as tags to make it easier for people in the lab to actually separate these and find these molecules when we're really testing, right? But the output of our model is a candidate drug, right? And sometimes, well, not sometimes, but almost always, we'll do a motive search, which basically means that we can screen these candidates for sort of short sequences of amino acids that we know have some effects, right? Usually adverse effects. So usually the motive is not something that you really want in your drug, right? So you have to kind of pre-screen it and discard all the candidates that have this sort of thing in their design, right? And so the central part is what I'll talk about, which we do with AI. And basically all this started with the advance of AlphaFold, but then other people picked it up while it was not public or open source the AlphaFold model, then people started playing with something called Rosetta Fold, which is basically an effort to recreate based on public data the same pipeline as AlphaFold uses, right? And these days, because we are trying to generate new things, right? We took a leaf out of the generative AI book, which is diffusion. If you know it, it's the way probably everybody knows of stable diffusion. It's a way we train generative models mostly for image generation. Here, we basically apply the same way, the same principle. And the idea is that if you want to learn a pattern of something, right, then you could kind of train the model by adding a bit of noise to the pattern. So it's sort of like trying to learn what the image should be without a little bit of the noise, right? Which everybody can do. If you do this iteratively and pay, take care of how fast you're adding the noise, the effect is that in the end you can just feed the noise in the model, and you get its best guess of an image, right? In this case, we feed the sequence of amino acids, right? We feed sort of this homologous template is a type of compound that we're kind of looking for. So it's not the backbone of the structure of the stuff that we want to get out, but it's a sort of in general vicinity of it. This is a sort of a standard trick of helping the model out by telling it, if you need to guess something, at least it's this type of a thing that you're guessing, right? You don't just do it blindly, right? And then there's also a 3D component to it, because these are chains in 3D. So it also needs to guess the coordinates, right? But once this is all trained on a lot of public data about the different compounds that we have the data for, right? We have a nice model that can actually, on a GPU, you can get 100 candidates for a drug, right, in an hour. And the other part, once we've done that, is a little bit tricky, right? So now we have sort of a shape and a backbone of the thing, but we need to find the exact order of amino acids to make something that works, right? And this is done by a message passing neural net, which is basically, it is related to graph neural nets, a little bit more complex, but it's an approach that's been proposed in 2017. Basically, you can think of it as the main approach of using neural nets in chemistry, right? And for complex compounds, right? So with this thing, it doesn't sound like a lot, but basically we can recover sequences 52% of the time, which is actually great, right? It's a science paper. And then once we've done all that, we have the candidates. Then with the folding, with the AlphaFold, and we were using AlphaFold 2 at the time because the AlphaFold 3 was not out then, or not open source then we would kind of look at the binding affinity, right? And we're kind of trying to get something in this region, because that means that the error fit between the thing, our lock and our key is the lowest, right? And these parts are a little bit, the score without the tag is something that of course you're looking for, but then it makes it, without the tag, it makes it hard to verify in the lab, right? So you have to add the tags to the part of it. They're going to change the shape of the molecule. So it's not always, as you see, that there's a linear correspondence between the score with the tag and without, you want to be somewhere there, right? Because this makes it both a good fit for what we want to solve, but also a good fit for what we can test easily in the lab, right? And this is just a sort of a comparison with in terms of RF diffusion that we are using and let's say the main competitor, right? And you'll see this error, affinity error is a little bit higher for this thing, and we really want to be there in a sort of 10 range for it, right? And these are the good candidates that we find. And actually, we for the committee over that we work for over the last year, we actually managed to find 10 new peptides that they're looking really, really good in terms of real tests, right? And so hopefully, yeah, I'm gonna fit the time. But what I wanted to kind of, it was just an overview of the things that could be done, not everything that is being done in the field of AI and applying to medicine. But it is a very promising field, both money-wise, but also, you can really make a difference, right? If our mammography thing works out in the end, we'll probably be saving a few thousand women in Serbia every year, right? If you do a new drug, nobody knows how many people you can touch, right? There are different AI approaches that have been deployed and that are being deployed. Some, different levels of maturity. Computer vision is something they are very used to, and kind of, if you can do it, then they'll happily use it, right? For us, the limiting factors, and I guess Juan told me about the project they're doing in CeADAR, it can be complex from the GDPR standpoint to gain access to data, right? And without data, it's really hard to train. It was actually a limiting factor for the big sort of drug design models that we use, right? Because a lot of the time they would be trained on proprietary big pharma data, and they could not be simply open source, right? The other part for us is that if you're going to do it, then you really have to have somebody in the domain to work with, right? And they need to be interested, and they tend to be overworked, right? So it's a little bit difficult. You should add like 20% of time and effort to your project, at least when working with the medical people, at least here in Serbia, right? And for us, we were faced with a sort of a weird paradox trying to apply it locally. So the medical guys are kind of not really, they don't believe, I guess they start from the south, that we are able to kind of provide viable alternatives to, internationally developed products. On the other hand, the citizens actually prefer stuff that is developed locally, so they trust it more. So it's a little bit of a balancing act right there. And with that, I'll share with you a few, Adobe Firefly generated thank you images.
Yeah, thanks Dubravko for a very interesting talk with many interesting applications of AI in medicine. So now we stop the recording and take questions.